In Chapter 7, we're going to start talking about applications of integrals. And for the first part here, we're going to be going back to our position, velocity, acceleration graphs. We first want to define a couple terms here. So what's distance and what's displacement? For our notes here, we can actually just cross off this first line here. We haven't actually learned that piece yet. And so I'm going to start with just the definition of displacement. Okay, oops. Displacement is just the change in position from when we start to when we end. And total distance is, how far have you actually been traveling the entire time. So just a little bit of an example here. Let's say we looked at the phrase 2 steps forward and 1 step back. So if you were to actually say, I'm going to start right here. I took 1 step forward and then another step forward. And then I'm going to change directions and take 1 step back. So that's where I finish. Okay, the total distance that I traveled, I actually burnt the energy to take 3 total steps. But my displacement, the difference between where I started and where I finished, is only 1 step. And so that's kind of the basic idea there. Now I want to connect that to maybe what we've been talking about with integrals and that idea of area under a curve, and that's going to help us with our later examples, I think. So let's pretend for a second that we're going to model the situation of 2 steps forward and 1 step back. And we're going to say that for the first 2 steps, I'm traveling at maybe 1 foot per second. So that would be kind of my velocity chart there. And so I did that for 2 seconds, traveling at 1 foot per second. So it took me, in 2 seconds, I traveled 2 steps there. And then from second 2 to second 3, now I'm going to be going backwards, so I have a negative velocity there. Okay, if I were to think about the entire area as far as like an integral, okay, this part here, whoops, that's way off. Okay, this has an area of 1, this has an area of 1, and this has an area of 1. So I add all 3 boxes together, I get 3. That's my total distance. But I think about integrals and having positive versus negative area, and I'd end up with an answer of 1, and that's displacement. So displacement means integrate from the start to the end, from 0 to 3 in this case, and total distance would mean integrate from 0 to 2, and then from 2 to 3, and add those 2 answers together. Make both things positive and add those answers together. Okay, so some formulas here. First of all, to find displacement, we just need to integrate from A to B. Our starting point is A, our ending point is B, and the reason it works out that way is because, if I were just to add on to this, we know that the antiderivative of velocity is position. Remember that position, we use an S. So we say the antiderivative is function S, and we'd have to still plug in B and A. And so that really is S of B minus S of A. If we actually follow through the math definition, we'd say when I integrate there, I'm going to take the ending position, what's going on at B, and subtract the beginning position, what's going on at A. And if we want to find that new location, we can just take these things and rearrange it. That's kind of what we've been working on with some of our free response questions lately. I could take the above statement here and rewrite it for S of B or S of A. So let's actually try to create a little bit more space here, but I could just take this statement that I have already and just rewrite it like S of B equals S of A plus, whoops, get my pen back there, okay. The integral from A to B of velocity. Okay, so I'm just taking this part here and this part there and just rearranging it to get that second piece. Okay, that's what we did in our free response questions in our previous chapter. Okay, let me zoom back here. Okay, and then finally, to find our total distance, we're just going to think about either the absolute value of that velocity equation or break it into chunks and just make sure that every single chunk we count as positive. Very simple, similar to what we call total area in Chapter 5. So let's go through a complete question that might relate some of these things together here. Okay, so example 2 says, suppose the velocity of a particle moving along the x-axis is given by 6t squared minus 18t plus 12, and we are just looking from the time of 0 to 2. First thing we're going to do is go back to first semester and just think about when is this thing going to move to the right, move to the left, when is it stopped, and it might be helpful just to get a picture of what this looks like. So if I look at the equation itself, I can tell that the y-intercept is going to be 12, and because it's a positive 6 times t squared, it has to open up. This parabola has to open up. So that's going to be kind of helpful. It might also be useful to maybe factor things out just a little bit. So I'm going to zoom here just to focus on part A. Okay, and if I was going to factor it out, first thing I notice is that I can take a 6 out of all 3 parts, and then once I break this quadratic into, if we unfoil it, I'm going to end up with this result right here. So putting it all together as far as graphing, I know that, and this is going to be very inexact, but I know the y-intercept has to be at 12. I know that it has to go through the x-axis at 1 and at 2, right, because that's when this whole thing would equal 0, and I know it has to open up. So I put all that together. I know it's going to cross through here, go something like that. And remember that we are just looking at the time from 0 to 2. So based on that and what we know from first semester, here the velocities are positive, so it's going to be moving right. Here the velocities are negative, so it's going to be moving left, and then at the x-intercepts it would be at 0. So this would kind of summarize my answer right here. This right here, just using those funny brackets to say just the points 1, 2. So sorry about the messy handwriting there. Okay, part B, for finding the displacement. Now I'm just looking at the overall. I want to know the change that has occurred from when I started to when I ended. And that's just going to be a normal integral. So again, I'm just going to shift things around here. As far as the notation, I'm going to be looking at the time from 0 to 2, and I'm just going to take whatever my velocity function was and integrate. Okay, so my velocity function was 6t squared minus 18t plus 12. And if I was to integrate that, I would get, let's see here, 2t cubed minus 9t squared plus 12t, and into that I need to plug a 2 and a 0. Okay, so we're going to do just a little bit of algebra here. Let me shift this over a little bit. Okay, I would get 2 times 2 cubed minus 9 times 2 squared plus 12 times 2. Oops, there should be a squared there. 12 times 2. Okay, so that's kind of my first chunk. And then from that I'm going to be subtracting. I'm plugging a 0 in, so it'll be a 0 minus a 0 plus a 0. Doesn't really do anything there. And so I just need to figure out what this first chunk is right here. Okay, and I just challenge you to try to do it without a calculator. See if you can. But 2 cubed would be 8 times another 2 is 16. 2 squared is 4 times a 9 is 36, so it'll be minus 36, and then plus a 24. Okay, and if you go through and you do all of that, you're going to get an answer of 4. So basically that means from the point that we started at to when we ended, the overall change in change in position was 4. If we started at 8, we ended at 12, or vice versa. Okay, part C is something that requires you to use your calculator. So I will show you that in class tomorrow, but the basic idea is to find the total distance. Okay, I want to use absolute value, and we'll talk about what that means tomorrow a little bit, but the general formula, we're going to integrate from 0 to 2 the absolute value of the velocity function, and that would equal 6. Okay, what that means here is we're going to take this equation that we started with here, we're going to be flipping this so it goes more like that, and then we can just find the area under the entire curve, and that would represent total distance now. That's what absolute value of a function does. It takes all that negative stuff and flips it up to the top. Okay, we can do that same thing algebraically though, and that's going to mean splitting it up into chunks, going from 0 to 1 and then from 1 to 2. This is going to be just a little bit of writing, so I'm going to pause, write a bunch of stuff down, and then kind of walk you through it. Okay, so look at all that beautiful writing there. So basically, we're going to look at the two separate chunks from 0 to 1 and from 1 to 2. And so when I integrate those two things, I get the same function that I used before, just have to use it twice. And the reason I have subtraction there is because I know this will get me negative area, so I need to make it positive in the end. So if this is going to be a negative number, I'm going to subtract it to make this entire thing be positive, and I can add it to my other positive answer. Okay, so when I plug in my 1 and 0 here, I'm going to get 5 minus 0. When I plug in my 2 and 1 right there, I get 4 and 5. And as I work through this, 5 minus 0 is 5. 4 minus 5 is a negative 1. So the area under that part of the curve, which is also under the x-axis, is actually negative 1. And I'm going to subtract it so that this all becomes positive. In the end, the total distance that was traveled would be 6. Okay, a lot of stuff covered there. Jot down any questions you might have, and we'll talk about it tomorrow in class.